Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is More Substitutions for Roots in Quadratics, including Combo Approaches. As always, please be an attentive learner while watching this video. By way of introduction, in this section, we're going to look at integration techniques that can be useful for some integrals with roots in them. Not always, but sometimes. We've already seen some integrals with roots in them, and some of those can be done quickly with a simple Calc 1 substitution, and some can be done with trig substitutions. However, not all integrals with roots will allow us to use these methods. And so we're going to look at a couple of examples, and you'll see another technique that can be used sometimes again to help with these integrals. So with the first example, we're going to look at evaluating the following integral. So this is the indefinite integral of x plus 2 divided by the cube root of x minus 3 dx. There is benefit in trying this because you'll understand the solution better, so I encourage you to give it a go. Let's see how you did, and if you solve this, congratulations. If not, you'll learn from what we're going over. All right, the a substitution that will work this time is letting u equal the cube root of x minus 3. We're not letting u be the stuff under the radical because that's not going to work. In this case, you will crash and burn if you did it. Now there is going to be more work, and in fact, here's what we're going to do. If u is equal to the cube root of x minus 3, that tells us that if I square both sides, cube both sides, I will have u cubed is equal to x minus 3, or x is equal to u cubed plus 3. If x is equal to u cubed plus 3, we know that dx is equal to 3u squared du. And so now we're going to substitute this into our equation. So instead of x, we're going to write u cubed plus 3 by this substitution. 2 is 2. And here you had the cube root of x minus 3, and that's just u. And here was dx, but dx is 3u squared du. So we have all of this. Now, what we're going to do then is we are going to be multiplying these things together. And so here you have u cubed, and this is times 3u squared. So that is going to be 3u to the 5th, but then I divide by u. So algebra tells me that is 3u to the 4th. And here the 3u squared is taken times the 5, and 3 times 5 is 15. That's u squared over u still, and so we get 3u to the 4th plus 15u, and then it's just du. This is easy. You add 1 to the exponent and divide by the new exponent, getting this in terms of u. But then we have to reverse our substitution, so we have to let u be x minus 3 to the 1/3 power. We substitute that in, and we have solved this problem. Here's another example. So what we have this time is a square root, but is the indefinite integral of 2 over x minus 3, and this is the square root of 10 dx. You know what to do. Let's see how you did. Well, the same technique will work. We're going to let u be the whole radical. Sometimes that works, sometimes it doesn't. Experience will tell you the more problems you do, you'll get better at this. But if u is equal to the square root of x plus 10, that means that x is equal to u squared minus 10. You just square both sides and solve for x. But if x is equal to this, that means that dx is 2u du. Okay, so now we're going to make this substitution up here. 2 is 2. We just leave that alone. This is x, but x is u squared minus 10. So I get u squared minus 10 minus 3, but this is u. Dx is du, 2u du, excuse me. So I put all of that stuff in. So now when I multiply across the top, I get 4u over. And then I simplify, and I'm rearranging this just a little bit so it is cleaner. This is u squared minus 3u minus 10. Now this integral, the degree of the numerator is less than the degree of the denominator. That means we can do this with partial fractions. And we have to factor the denominator, so we factor this into u minus 5 times u plus 2, and then we use the Heaviside cover-up theorem or other ways to solve for a and b. And so we find out that a is 20 over 7 and b is 8 over 7. Make sure you verify these calculations when you go through. So this integral that we started out with our substitution is, here is a, 20 over 7 over u minus 5, and this is b, 8 over 7 over u plus 2. Well, this is partial fractions. Each of these integrals will yield a logarithm of the absolute value of u minus 5. That's 20 over 7 times that. We just pull that out. 8 over 7 times the natural logarithm of the absolute value of u plus 2. Plus c, because it's an indefinite integral. And then because it is an indefinite integral, I have to go back and I have to substitute what u is. And u is the square root of x plus 10. I just substitute that in everywhere I have u, and this is the final answer to the problem. Now, we'll spend a little bit of time talking about some other applications, but now we're going to go back and really talk about quadratics. Now, by way of introduction, we've actually done a lot of quadratics already. We've integrated things like this. You let u equal the denominator, and you have du more or less up here. And so this integral becomes 1/2 the natural logarithm, the absolute value of x squared plus or minus a plus c. Similarly, we have this one. We remember that this is the arctangent, and this is 1 over a times the inverse tangent instead of arctangent x over a plus c. We also saw integrals that look like this. That was where we substituted the secant. This where we substituted the sine, and this where we substituted the tangent, and so we could use those with trig substitutions. But not all integrals are like this, because these are missing an x term. All of these examples are missing the middle term, and so some integrals are not missing this, and so those are different. They can't be used with this technique. Now, some of them that do have an x term are easy to do. This one, for example, if I let u be the bottom, then the top is well, if this is the if you let this be u, then du is 8x plus 12, which is a multiple of 4 of the top, so that's easy to do. You do a u substitution, and you have du over u fundamentally, and with the constant you get this as an answer. And other integrals with quadratics in the denominator can be done with partial fractions, like this one. And you can factor that denominator into 3x plus 1 times x plus 5. Use Heaviside and you get 4n minus 2. You can integrate each of these, getting logarithm terms, and you have that. Unfortunately, these methods don't work on all integrals. Again, in this class, there's a lot of different ways to approach problems. A simple substitution will work only if the numerator is a constant multiple of the derivative of the denominator, and partial fractions will only work if the denominator can be factored over the field of real numbers. But often, combination approaches will yield fruit, as more examples will demonstrate. So let's look at an example. So I'm going to ask you to please evaluate the following integral. It is the indefinite integral of, this is the square root of x squared plus 4x plus 5 dx. Again, you benefit from trying these, so give it a go, please. Let's see how you did. And if you did it, congratulations. If not, you'll learn from going through the example, and you'll be prepared to learn. Now what we're going to do is we're going to use the technique of completing the square underneath the radical. So notice that x squared plus 4x plus 5 is the same as x plus 2 whole squared plus 1. Now that happens because if I expand this binomial, I get x squared plus 4x plus 4 plus 1. So that's x squared plus 4x. I have the 1, and then the 4 gives me 5. So these two things are actually equal, and this is going to be of the form u squared plus 1 squared, which makes you think this could be a tangent substitution. So we're going to let this thing that I could talk about being u, but I'm just going to say x plus 2 is equal to the tangent of theta. Now I'm going to solve here. So x is equal to tangent theta minus 2. And that means that dx is the derivative of the tangent is the secant squared theta d theta. So that means that this radical becomes, by this substitution, tan squared plus 1. Underneath the radical I have secant squared. I'm taking the square root of that. That's the absolute value of secant. But realize that when we're doing an indefinite integral, we don't worry about the absolute value signs, although we do in definite integrals. Okay, so what we have is that this square root thing is secant theta. So when we do the substitution, we get secant theta, but then we have secant squared theta in the dx. That means this is the indefinite integral of secant cubed theta d theta. Now perhaps you remember this, but we've actually done this integral multiple times before. We did integration by parts, and we found back in the chapter on integration by parts and also on trigonometric integrals that this is going to be 1/2 secant theta tan theta plus the natural logarithm of secant theta plus tan theta whole plus c. Now we said that x plus 2 is tangent of theta, and this is an indefinite integral, so we actually have a triangle again. So the tangent of theta is equal to x plus 2. So what that means is here is theta, and the tangent is the opposite over the adjacent, so that is x plus 2 over 1 is tangent theta, and we can use the Pythagorean theorem to get that this is x plus 2 whole squared plus 1 squared, and you take the square root, that is this side. So you see 1/2, the secant is the hypotenuse over the adjacent, so I'm substituting that for the secant. The tangent is x plus 2, so you see I'm getting 1/2, and this is that square root over 1 times x plus 2 plus the logarithm of the secant. Again, the secant is this, and the tangent was this, plus c. Make sure you understand that, but you see we've changed things back into native variables, and we are good to go. Here's another example for you to consider. Evaluate the following integral, the indefinite integral of 1 over 2 x squared minus 3x plus 2. Again, there will be benefits for you giving this a go. And so I'm asking you to give this a go, and we'll see how you do when we pick up the second half of this video. So give it a go. Now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.